So, what if the secret to building a truly brilliant AI isn't just about making it bigger? What if it's about fundamentally rewiring the way it thinks? Well, today we're going to dive into a new paper that does exactly that. It's a breakthrough that changes the very pathways information travels inside an AI's quote unquote brain.
All right, let's start with a really basic but super important question. We all know AI models learn in layers, right? They build up knowledge one step at a time. But how does that final layer, the one making the decision, actually remember some brilliant little insight that the very first layer came up with? How does that initial spark even survive the whole journey?
Here's a great way to think about it. Imagine an AI is like a giant skyscraper. Each layer is a new floor, processing ideas and adding its own spin. Now, the problem with most of today's designs is that by the time you get to the penthouse on the top floor, those incredible insights from the ground floor, they've faded into just a muffled whisper. And this right here is the core problem. Researchers call it the information bottleneck. It's basically a traffic jam for ideas, and it's a huge issue.
Okay, so the way information usually travels up this skyscraper is through something called a residual connection. Just think of it as a single running document. Every single floor just adds its new thoughts to the bottom of the page. You can see how that would become a giant, messy pileup of information, right? And this quote from the researchers just nails the problem. Early information gets completely buried in the noise. And get this is the wild part. It gets so lost that you can literally just delete a huge chunk of the middle floors of the skyscraper, and the AI barely even notices. That's how little they're actually contributing to the final result. Now, this slide shows a really weird side effect of that pileup. In order to be heard over the noise of all the previous floors, the later layers, they basically have to shout their ideas. You can see their outputs just get bigger and bigger and bigger. This can make the whole learning process unstable. It's like being in a conversation where everyone just keeps yelling louder and louder to be heard.
So, the big question is, how do you solve a massive architectural problem like this? Well, it turns out the solution wasn't some brand new invention, but actually a really clever twist on an old idea. And here it is. This is the big aha moment of the paper. The researchers realized that this problem of losing information through the depth of the model, going up all those floors, it looks almost exactly like a problem we've already solved, losing information over the length of a sentence. Yeah, just think back to those older AI models like RNNs. They'd read a really long sentence, and by the time they got to the end, they'd totally forgotten what the beginning was about. The solution that changed everything for AI was, of course, the attention mechanism. It gave the model the power to look back at any word in the sentence whenever it needed to. So the researchers thought, hey, what if we apply that same attention idea, but not across a sentence? What if we apply it up through the layers of the AI itself? What if we could give each and every layer its own voice? And this slide just lays out the difference perfectly. On the left, you've got that blind, messy pileup we've been talking about. But on the right, with this new method called attention residuals, each layer becomes a smart agent. It can look back at any previous floor and intelligently pull exactly the piece of information it needs for its job. It's not a pileup anymore. It's more like a library. So here's basically how it works in 4 steps. First, a layer decides what kind of information it needs. That's its query. Then it scans all the outputs from the previous layers. Third, it assigns importance, or weights, to the bits of information that are most relevant. And finally, it builds its own custom summary for itself. No more messy, one-size-fits-all document. Now, this idea is absolutely brilliant in theory, but in practice, there's a huge problem. I mean, giving every single floor of the skyscraper a direct phone line to every single other floor, that would be a complete computational nightmare, especially for the massive models we train today. And the paper is super upfront about this. When you're training a model across thousands of GPUs, the thing that costs you the most isn't the calculation, it's the communication between all those computers. Forcing every layer to access every other layer's output creates an absolute data traffic jam. So their incredibly clever solution to this traffic jam is a more practical version they call block, at, and res. Instead of a free-for-all where every floor can call every other floor, they group the floors into blocks. Now layers only need to pay attention to the high-level summaries from each of those blocks. So here's how that works. Let's say you take a 128-layer model. You group it into, say, 8 blocks. Now inside each of those blocks, information gets passed along in the old, efficient way.
But between the blocks, the layers use that smart attention mechanism to pull from the other block's summaries. It's this beautiful compromise that gives you the efficiency of the old system with the intelligence of the new one.
And this table really just shows the payoff. Now, don't worry about the math symbols. All it's really saying is that the cost of that full unrestricted version grows with every single layer you add to your model. But with the block version, the cost only grows with the number of blocks, not the number of layers. And since they can use as few as, 8 blocks, it becomes massively more efficient and actually practical.
Okay, so the engineering is really clever, we get it. But does it actually work? Does it make the model better? Let's take a look at the results.
Well, here's the headline result right here. A model built with this new method achieved the same performance as a standard model, but with 25% less training compute. Let me say that another way. You get the exact same amount of smarts for a whole lot cheaper. That is a huge, huge deal.
And it's not just about being more efficient, it's about being more capable. On a really tough, graduate-level reasoning benchmark called GPQA Diamond, the attention residuals model jumped from about 37% accuracy all the way up to over 44%. That is a massive leap in complex reasoning ability.
And the benefits really were seen across the board. As you can see here, the new architecture just got better at pretty much everything, but especially at complex reasoning and writing code. And maybe most importantly, it fixed those underlying technical problems we talked about at the beginning. No more shouting to be heard, and a much smoother flow of information during the learning process. Okay, so let's zoom out for a second. What does all of this really mean for the future of how we build AI?
Well, we're back at our skyscraper. I think the big takeaway here is that building a truly intelligent system isn't just about adding more and more floors. It's about designing smarter elevators. How information actually flows and connects between all the different layers is just as important, if not maybe even more important.
And that leaves us with a pretty fascinating final thought. For years, so much of AI research has focused on making the floors of the skyscraper smarter. This research proves that just by redesigning the elevators, the connections between them, we can unlock these massive gains. So it really makes you wonder, what other fundamental parts of the AI blueprint are just sitting there, waiting for someone to come along and completely rewire them?